So thank you, Natalia, for the great introduction. So today I want to tell you about the interconnects and the technology, the hardware technology that New Quantum is developing to support fault-tolerant scale quantum computers. So to scale to commercially useful sizes, I think more and more people recognize that there's going to be some kind of modularity where people and quantum computing companies will build QPUs as large as they see fit, and that QPU size would probably depend on qubit modality, but then it will be advantageous to sort of introduce non-local connectivity thanks to optical interconnects to really scale the system further. And the issue is the technology to produce links between different QPU has so far not been demonstrated to the scale that and the performance that we need today. So at New Quantum, we're focused on providing a solution for an efficient network layer. And in particular, once you go to optical frequencies, you can support long-range connectivity on the scale of your system. And what that gives you access to is efficient QEC codes. So we've talked about quantum LDPC codes. What's not said about these codes is that they always require some kind of connectivity on the scale of your system size. And that's going to be a very slow link if your only plan is to shuttle your qubit. So what does that system look like? At New Quantum, we like, sort of crayon diagrams and how we think about the hardware that will be needed to instantiate this network layer is highlighted here. So first of all, adjacent and integrated with the quantum processing unit, you need some kind of very efficient qubit photon interface. This is an interconnect to produce high rate, high fidelity qubit photon entanglement. And then the idea is that you'll need to build above these a switch layer. What our architecture work tells us is that we actually think that we only require sort of a handful of connections between one QPU and any other QPU. But importantly, once you go to the optical domain, you can easily provide connectivity on that length scale of the system size. And so we believe that the distributed quantum architecture can be really intrinsically modular with using only low depth switches. And then the proposal, of course, that there are other ways to achieve this. But if you want to keep it simple and keep it high fidelity, we foresee creating these distant entanglement links via the simple Bell state measurements, a beam splitter, and 2 detectors. And so at New Quantum, we've been working on developing this sort of switch layer. Our first prototype has been released recently, a first quantum networking unit, which has been designed to support connectivity between 4 quantum nodes. And the system that we've built will allow you to create any 2-node entanglement with less than 6 dB loss in entanglement rate, and will introduce less than 2 × 10⁻³ error or 3 × 10⁻³ error, worst case scenario. We've worked really hard as well on the control layer. So we've heard earlier how we had collaboration, really fruitful collaboration with CERN to distribute timing between the different nodes. And we've also achieved very low control latency, so the hardware latency between the point where you detect entanglement and you sort of react to it. We're also working on, our next generation of devices, making things more scalable. So for this, you need to use integrated photonics. And so at New Quantum, we've been developing these low-loss switches out of thin-film lithium niobate, and we've already achieved losses of 0.5 dB per switch with very, very low switch crosstalk, better than 30 dB, and up to 35 dB we've measured, which do mean that we can, with this generation of device, hope to achieve much better entanglement rates, but also reduce the error introduced by this switch layer. And the other key element for the Bell state measurement is the development of waveguide integrated SNSPD to do this on-chip detection, which is, again, something that we are developing at New Quantum. Having the switch layer is great, but really, as we heard earlier from Hermann Hauser's talk, it's also really important to have the rates. To support distributed quantum computing and distributed error correction, the network layer at a high level needs to be a sort of like Bell state factory with a certain rate that will not slow down the computer as a whole. We've done some work looking at the ion modality in particular. And for this modality, for example, this Bell state generation rate between QPU has to be on the order of 10 kilohertz. Of course, fidelity is still just as important. You really need to target fidelities which are, on order of, well, our QEC models, C-Coral's talk, tell us that we can go all the way down to 2% errors on the long distance links. But fidelity is also critical. So how do you achieve rate? New Quantum's approach has been heavily focused on qubits, which can already emit photons. And then our approach is to use Fabry-Perot microscopic cavities, which means that you have an optimal geometry where you have a strong light-matter interaction, but without bringing cavity mirrors close to your qubit. And so we've produced our first qubit photon interface for neutral atoms in 2024. This is the module that you see on the right. All the cavity alignment was passive in XY. We only had one tuning knob to be able to tune the cavity length and the cavity resonance to the atomic qubit. We also showed that we could actively stabilize this cavity, which was integrated in a UHV environment successfully with this XY alignment being really maintained throughout. On the ion side, we're also really interested in demonstrating that these cavities can be interfaced with ions. For ions, we've, since the 2024 Atom module, we've improved massively the quality of our microcavities. So we reach finesses on the order of 100,000 when we are loss limited. And we have created our cavities at the tip of tiny substrates that we integrate into the ion trap that you see on the left. This time we're doing the UHV packaging ourselves, and we've already shown a turnkey lockbox solution which allows us to lock these cavities with 10% transmission noise, which we aim to reduce to 1%. So where are we at? Right now, New Quantum has built all the building blocks to be able to set up a quantum network testbed, and we aim in the next 2 years to demonstrate 50x improvement in entanglement rates and state-of-the-art fidelity, with some degree of autonomous operation, as you'd expect. But more importantly, looking at the future, we need these interconnects to be scalable. This scalability effort is well underway for the switch layer using PIC. And for the qubit photon interface, similarly, we are also starting to work with foundries, for example, Infineon, and we are at the early stage de-risking material processing and on wafer processes. So with that, I'm slightly over time, so I'd like to thank you for your attention.